Hi everyone, today I'm presenting FuzzGen Automatic Fuzzer Generation that was published at SEC’20 2020, and the core question of this paper answers is, can we automate the process of writing fuzzers for software libraries, something up until this point required weeks of expert effort per library? So before we get into FuzzGen specifically, let's make sure we're on the same page about fuzzing. Fuzzing is a dynamic testing technique that finds vulnerabilities by throwing large amounts of semi-random input at a program and watches for crashes. The core loop is generate or mutate an input, feed it to the target, monitor for crashes, save anything interesting, and repeat, thousands of times per second. The modern version of this is coverage-guided fuzzing, used by tools like AFL and libfuzzer. These tools instrument the binary so that every time an input reaches a new code path, it gets saved and mutated further. That feedback loop is what makes fuzzing so effective at finding deep bugs. So, where does FuzzGen fit in the fuzzer taxonomy on the right? It's not the fuzzer itself. It's the tool that generates the stub that makes libfuzzer applicable to a library. It's one layer above the fuzzer. Before FuzzGen, the state of library fuzzing was pretty grim. Let me give you some context. In 2015, the stage fright vulnerability hit. Researchers found a set of bugs in Android media parsing library, libstagefright, that let an attacker execute code just by sending a victim a malicious MMS message. No click required. Up to 950 million Android devices were vulnerable. The root cause? Complex parsing code with zero fuzzing coverage. Google's response was OSS Fuzz in 2016, a continuous fuzzing service for open source projects. But here's the catch. To fuzz a library well, you still needed someone to write a fuzzer stub by hand. These were really only two approaches before FuzzGen. First, run AFL through a consumer application that uses the library. This works, but you're fuzzing the whole app at once. Coverage gets diluted, and you spend a lot of time fuzzing application code rather than the library. Second, write a manual libfuzzer stub. This produces the best results, but it takes weeks per library, requires deep API knowledge, and simply doesn't scale to hundreds of libraries. Fudge, published at FCE in 2019, was a first attempt at automation. It extracted short code snippets from a single consumer to build small fuzzers. FuzzGen, published a year later, goes much further. It merges multiple consumers into one unified graph. So, why is library fuzzing specifically hard? Libraries cannot run standalone, meaning there's no main function to throw an input at. You need a fuzzer stub that calls the right API functions in the right order. The problem is that API dependencies are implicit. Library functions share state through APEC context objects, and the correct call order is documented at best, but never formally specified. Looking at the example on this page, you can call at least 4 distinct setup functions: get memory, count, allocate fill records, align memory, before you can code a single frame. A random fuzzer will almost never stumble into that valid sequence by accident. And if it doesn't, 2 bad outcomes. Either you crash immediately on an invalid state check, a false positive that isn't a real bug, or you terminate early and waste your entire fuzzing budget. The scale problem on the right makes this worse. Ecosystems like Android and Debian have hundreds of libraries. Writing a fuzzer for each manually is completely infeasible. What if we could extract valid API usage from programs that already use the library? That's the question that FuzzGen answers. Here's FuzzGen's key insight. The answer is already in the system. Existing programs that use the library, called library consumers, already demonstrate correct API usage. They set up state properly, call functions in the right order, and pass return values where they need to go. FuzzGen mines those usage patterns through a whole system static analysis and synthesizes a fuzzer from then automatically. The pipeline has 4 steps: infer the API, build an abstract API dependence graph, analyze argument values, and synthesize the fuzzer. The output is a libfuzzer stub, a C++ file that calls the library's API in valid ways while injecting random input. A key selling point, FuzzGen generates a fuzzer in minutes. A human expert needs weeks and may still miss edge cases that real programs already handle. So, step 1 is figuring out what the library public API actually is. FuzzGen computes this as the intersection of functions implemented in the library and functions declared in the header files that consumers include. The logic is, if a function is in a library but no consumer ever includes its declaration, it's not reachable through attacker's controlled input, so there's no point in fuzzing it. There's also a progressive verification step. Each candidate function is tested by actual trying to compile it and link against it. If linking fails, it's not really part of the API. The whole thing runs as an LLVM/Clang analysis passed during compilation. Notice the LibrePost example. The library has 276 total functions, but only 65 qualify as API, and consumers in practice only call 12 to 56 of those. Think about why fewer consumers used API calls could actually be better for a fuzzer. Because the fuzzer stays lean and stays focused on the most used, most exposed parts of the API. Those are the same parts an attacker would target. Step 2 is the heart of FuzzGen, building the abstract API dependence graph, or A²DG. Think of it as the skeleton of a library consumer. You strip away all the application login and keep only the API call and the relationship between them. Each node is one API call. Each edge is control flow between the two API calls, annotated with valid parameter ranges. The graph captures two types of dependencies. Control dependency, which is opus decoder create, must happen before opus decode. And data dependencies, the decoder handles returned by create must be passed to every subsequent call. FuzzGen builds this by starting with the consumer's full control flow graph, which might have hundreds of blocks, and iteratively removing every basic block that doesn't contain an API call. It also inlines non-API function calls recursively. So if a consumer calls a helper function that calls an API function, FuzzGen reaches that API call too. The whole thing runs using LLVM link time optimization, so it can analyze across module boundaries. Here's what this looks like concretely from the LibrePost consumer. You can see the clean A²DG, get packet, bandwidth, get number of channels, create the decoder, run control and decode operations, then destroy it. That's the valid API sequence extracted from a real consumer. On coalescing, every consumer produces its own A²DG. FuzzGen then merges them into a single unified graph to capture more API interactions. The merge rule is strict. Two graphs can only be merged if they share a common node, meaning the same API call with the same argument types. This requirement is what prevents the fuzzer from constructing completely illegal API sequences. But coalescing isn't perfect. The paper calls this the state of inconsistency problem. Imagine one consumer shuts down a socket for reading, and another consumer later reads from it. If you coalesce those, you get a fuzzer that does both, which is invalid. FuzzGen enables coalescing by default, but lets analysts turn it off. If a false positive a crash problem, the cost is analysis time during triage. Every crash report needs manual verification. But the paper argues the coverage and bug finding benefits outweigh this cost. So, step 3, figuring out what to actually fuzz. Here's the memcopy problem. If you randomly fuzz the size parameter n, it becomes inconsistent with actual buffer size, and you get crashes that aren't real bugs. If you fuzz the destination pointer directly, you get seg faults. Neither of those is useful. FuzzGen classifies every argument with an attribute. Arguments get labeled as invariant, this is a context handle, don't fuzz it, random, go wild, array size, keep this consistent with the buffer it describes, output, which is this is a destination buffer, and don't read from it, and so on. You can see the full set of attributes on the right. The analysis runs in two directions. Internally from the inside from inside the library and externally by backward slicing through all consumers. When there's a conflict, external wins. Real consumer usage reflects ground truth better than static analysis of the library alone. Which attribute is most important for preventing false positives? Invariant. Preventing the fuzzer from corrupting context handles is what eliminates most spurious crashes. Finally, step 4, turning the A²DG into actual C++ code. The challenge is that the A²DG might have loops and complex branches. If you encode every possible path as a conditional in the fuzzer, it slows everything down, and fuzzing needs to be fast. FuzzGen's solution is to flatten the A²DG, remove backward edges to make it acyclic, then topologically sort it to produce ordered groups of functions. Within each group, the fuzzer's random input bits decide the call order. The key insight is that libfuzzer is a learning system. It tracks which inputs reach new code coverage and mutate those inputs further. So the fuzzer effectively learns which bits correspond to interesting API paths and focuses mutation there. You got breadth across the API and depth within interesting paths. FuzzGen has a choice to make. Which consumers do you use and how many? More isn't always better. If you throw 15 consumers at libpost, FuzzGen produces an 8,375 line fuzzer. It found a crash, but tracing back through 56 API calls to verify whether the crash is real or a false positive from invalid state is extremely painful. This paper introduces a metric called consumer density, the number of distinct API calls divided by the total lines of real code in the consumer. High density means the consumer is tightly focused on the library, not just calling it incidentally from deep in an application. Empirically, the sweet spot is the top 4 consumers by density. Look at the scaling table for libpost. At 13 consumers, you have 56 API calls covered and 883 graph nodes. At 15 consumers, still 56 API calls, 885 nodes. The A²DG has plateaued. New consumers just repeat API calls already in the graph while adding complexity and false positive risk. The plateau is your signal to stop. How would you decide the optimal consumer count for a new library you've never seen before then? You'd plot API coverage against consumer count and look for the knee of the curve. On the implementation side, FuzzGen is about 19,000 lines of code, 19,000 lines of C++, built entirely on LLVM. Everything operates on LLVM intermediate representation, the compiler's internal language, rather than the source code directly. This matters because it's language agnostic. C and C++ both compile down to LLVM IR, and FuzzGen handles both. There's one interesting engineering challenge, though. Converting source code to IR is lossy. Pointer types, array sizes, argument names, struct layouts, all of that gets simplified away during compilation. FuzzGen adds a pre-processing pass that runs before the IR is generated to capture this high-level information, because the code generator needs it to produce readable, correct C++. The final output always follows the same libfuzzer contract you can see in the code snippet. One entry point called LLVM fuzzer test1 input, and it calls in group 1, processing calls in the middle group, teardown at the end, compiled with address sanitizer to catch memory errors. For evaluation, the author chose codec libraries specifically because they're high risk. StageFright showed that media parsing libraries reachable from network input on Android are a goldmine for attackers, and because complex parsing code is likely to harbor memory bugs. 7 libraries were tested, 5 from Android, 2 from Debian. Each fuzzer was run 5 times for 24 hours each. Running 5 times is important as a single fuzzing run can be misleading because fuzzing is non-deterministic. Coverage is measured using sanitizer coverage and compared with the Mann-Whitney U-test for statistical significance. Note that the 3 video libraries have a single dispatcher API function. Every operation routes through one call. That's a particularly hard case for FuzzGen, and That's why the authors chose to deliberately stress test the system. Code coverage. The headline number, 54.94% average edge coverage for FuzzGen versus 48% for manually written fuzzers, about a 7 percentage point improvement overall. But the per library breakdown tells the real story. On the 3 libraries, FuzzGen wins by a massive margin, 15 to 20 percentage points. These are libraries with complex APIs, where FuzzGen's breadth really shines. It explores API interactions that a human analyst writing a focused stub simply wouldn't think to include. But on the 3 libraries, the manual fuzzer wins. For the library GSM, the manual fuzzer was already at 75%. There's simply not much room left to improve. For VPX and AOM, the manual fuzzer use loops that decode multiple frames per input, building up richer decoder state that trigger deeper code paths. FuzzGen's loop-free design is a real limitation here. The statistical test shows FuzzGen is significantly better for 6 of 7 libraries. Library AOM is the only one where the difference isn't statistically significant. So, should we prefer high coverage or high bug count? Can these diverge? Well, yes, and this paper is a great example. FuzzGen achieves better coverage but found fewer total bugs in some libraries. A focused manual fuzzer can repeatedly hammer a known bug decoder path and rack up the crashes. FuzzGen explores more but hits each area fewer times. Coverage and bug count are correlated but not the same thing. In terms of real-world impact, 17 previously unknown bugs, 6 CVEs. 4 are critical, all in library HEVC. These include heap and stack buffer overflows that could allow arbitrary code execution. The CVE 13187 is a high severity out-of-bounds read causing denial of service, and CVE 0858 in library AVC turned out to be a duplicate of a previously known bug, which is actually a useful sanity check that the tool is working correctly. What makes the CVE severity so high is that these bugs where these bugs live. The Android Media Framework. Media files are processed automatically in the background when received. You don't need to open them. That's the stage fright attack class all over again. All bugs were obviously responsibly disclosed, fixes were pushed upstream, and the source code was released publicly on GitHub afterwards. So, let's look at one CVE in detail to make this concrete. CVE 2106 is a stack buffer underflow in library HEVC's SAO's processing code, sample adaptive offset, a video filtering step. The vulnerable code is right here. There's a fixed size array called AU1_mask, and 2 writes use WD-1 and WD-2 as indices. If the fuzzed input produces WD equals 1, then WD-2 is -1, an index before the start of the array. That's a write to stack memory you don't own, which is a potential arbitrary write primitive on most architectures. What makes this interesting from a fuzzing perspective, you can only reach the SAO code if the HEVC's decoder context was fully initialized first. A naive fuzzer that doesn't set up the state machine correctly will never get here. FuzzGen got here because its A²DG encoded the full initialization sequence extracted from a real consumer. CVE 13187 on the right is similar. Malformed slice data sets an error flag, which then triggers a null pointer dereference during NAL unit parsing. Again, you need a valid decoder context to get to the slice parser in the first place. So, let me put the trade-offs side by side. FuzzGen's strength are the breadth and scale. Higher average coverage coverage. It considers all real-world API usage patterns, and it generates a fuzzer in minutes rather than weeks. Those are genuine advantages. And at the scale of Android or Debian, the time difference is the difference between fuzzing everything and fuzzing almost nothing. But manual fuzzers have their strength too. They can use loops, decode 1,000 frames per minute, building up a rich decoder state with iteration. They're smaller and easier to audit for false positives, and in 3 of the 7 libraries, manual fuzzers found more total bugs, specifically because they targeted known vulnerable decoder paths directly. FuzzGen's limitations are also real. Static analysis over approximation causes false positives. Coalescing can create invalid API sequence, and the quality of your output is only as good as the consumers you picked. The LibrePost situation is a good example. All 4 selected consumers focused on decoding, so encoding functionalities was completely untouched. The key insight is that these aren't competing approaches, they're complementary. FuzzGen is giving you broad coverage quickly across the whole API, while manual fuzzers then deep dive into the specific areas FuzzGen flags as interesting. So, would you use FuzzGen first and manual fuzzers second, or the other way around? Well, the paper argues that FuzzGen first. Use it to map the territory, then write targeted manual fuzzers for the areas that look more vulnerable. A quick tour of where FuzzGen sits in the literature. Coverage-guided fuzzers like AFL and LibFuzzer are the foundations, great for standalone programs, not directly applicable to libraries. FuzzGen generates the stub that makes library fuzzer work on any library. The closest related work is Fudge, published in SE in 2019, about a year before FuzzGen. Fudge also mines API usage from consumers, but it only looks at one consumer at a time and extracts short code snippets, what the paper calls a one-to-N approach. One consumer, many small fuzzers. FuzzGen's M-to-N approach merges multiple consumers into one unified A²DG, which gives broader API coverage at the cost of more complex graphs. Diffuse from the CS 2017 does interface-aware fuzzing for Linux kernel drivers. Drivers have a well-defined IOCTL inference that makes this traceable. FuzzGen tackles the harder case of arbitrary library APIs with no formal interface specification. And there's a whole line of work on API specification mining, API SN, MOPS, SSLint, that infers correct API usage to find violations. FuzzGen borrows ideas from the space but uses the mine specs for test generation rather than violation detection. FuzzGen's unique contribution is the M-consumer, whole system A²DG that synthesizes complete library fuzzer stubs with complex state management. Fully automatic, no humans in the loop. So, the paper is honest about its limitations, and there's 3 that stand out. First, false positives. The static analysis over approximate paths and coalescing can create invalid API sequences. The authors manually verified all crashes in their evaluation, but at ecosystem scale, that triage burden becomes significant. Second, loop-free fuzzers. FuzzGen flattening removes loops, but for video decoders, decoding multiple frames per input is essential for building up the deep internal state where the bugs hide. This is why FuzzGen loses on library VPX and library AOM. Third, consumer quality dependence. LibrePost only reaches 39.99% coverage because all 4 selected consumers focused on decoding. Encoding, packet manipulation, and repacketization were all untouched. This isn't a flaw in FuzzGen's design, it's a limitation of the consumer selection heuristic. The open research question on the right are genuinely interesting, and coalescing trade-offs is the most fundamental. Without coalescing, you get perfect precision but miss bugs that require interaction between multiple API usage patterns. While with coalescing, you get more coverage but also more false positive. That's the classic precision recall trade-off in program analysis, and that's just how it is. If you were extending FuzzGen for a thesis, which limitation would you tackle first? My vote would be for loop synthesis. Being able to generate fuzzers that decode multiple frames per input would directly fix the case where FuzzGen loses to manual fuzzers. So, why does this paper matter beyond the 17 bugs that it found? First, Android media parsing is the highest risk remote attack surface on the platform. StageFright proved that a library vulnerability reaches for MMS message can compromise nearly 1 billion devices with 0 user interaction. FuzzGen directly targets the attack class. Second, there's a scalability story. Before this paper, fuzzing a new library meant weeks of expert work. After minutes at the scale of Debian or AOSP, hundreds of libraries, that difference is the difference between fuzzing everything and fuzzing almost nothing. Third, A²DG abstraction is a genuine contribution beyond fuzzing itself. It's a clear, formal representation of the API usage that could be reused for API misuse detection, automated documentation, generation, or test synthesis in other contexts. And fourth, FuzzGen is part of a broader trend in security research toward using program analysis to automate tasks and used to require human expertise. OSS Fuzz for continuous fuzzing, CodeQL for automated vulnerability queries, and LLVM sanitizes for automatic bug detection. FuzzGen fits squarely in that lineage. Finally, key takeaways. 4 things to take away from this paper are 1. Library fuzzing requires API-aware test drivers. Random function calls don't produce real bugs. They produce false positives from invalid state. You have to set up the library correctly before you meaningfully fuzz it. 2. Existing programs are an oracle. Programs that already use a library and code validate API usage patterns. You don't have to figure out the right clause sequence from documentation. It's already demonstrated in the codebase. 3. The A²DG is the core contribution. It's the data structure that makes everything else possible, a graph abstraction that captures both control and data dependencies across API calls, enabling automated synthesis of valid fuzzer stubs. And 4. Coverage and bugs found don't always move together. FuzzGen achieves better average coverage, but have found fewer total bugs in some libraries. Breadth and depth are different things. The right answer for a serious security program is probably both. FuzzGen for coverage, targeted manual fuzzers for depth in high-risk areas. And that's FuzzGen. To leave you with a one-sentence summary, FuzzGen mines valid API usage for existing programs, builds an abstract API dependence graph, and automatically synthesizes libfuzzer stub that achieve higher code coverage than manually written fuzzers without any human interventions. Thank you.